How do we perform vector operations? Well, operations are things like addition, subtraction, multiplication, division. We won't be able to do all of those, but we'll do some of those now. A vector is a quantity with magnitude and direction, something like this. It has a size as well as, oh, this is pointing down. A scalar is a quantity with magnitude only. So something like 3. You can think of this as the difference between mass. Mass is a scalar, whereas weight is a vector. It's always pointing down. It's the strength of a force, and the direction of the force is always down. Whereas mass is just how much stuff there is. There's no direction to the stuff that exists. Summary. For scalar multiplication, we're going to distribute the scalar, the number, to each component, each part of the vector. And for vector addition, we're going to add corresponding components. So let's look at what this looks like. Scalar multiplication. These are 4 scalar multiplication problems. They're all technically the same scalar multiplication problem, but I'm showing you all the different notations that you could see. So the first one we see is we would distribute the 6 into both components. So we would do 6 times 3 and get 18. We would do 6 times 4 and get 24. So scalar multiplication is just distributed into each component. Here, same idea happens. 18 I hat plus 24 j hat. Here we have matrix notation. 6 is being multiplied into both of these, so 18 and 24. And lastly, if I tell you that here's a vector v, and I'm going to multiply it 6 times, well, what I can do is I can take that vector and make 6 copies of it, lining them straight up, tail to head. So 1, 2, 3, 4, 5, 6. So this entire vector, I'm going to make this a different color just so that it's obvious what I'm talking about. From here up to here, this entire vector would represent vector u. So all of these represent scalar multiplication, taking this vector and multiplying its length by 6 or distributing it into each of the components. Now, it might not be obvious why these are the same. The reason why they're the same is because essentially what's happening is the x component is being multiplied by 6 to become 18, and the y component is being multiplied by 6 to become 24. But you can just treat it as multiplying the vector by 6. Vector addition works by combining corresponding components. So x components are going to be added, y components are going to be added. So we take 3 plus 2, and we'll get 5. We'll take 1 minus 3 and get negative 2. So that is the sum. Here, we take the I hat, the I components. 3 plus 2 is 5 I hat. And then 1 minus 3 is negative 2 j hat. If we are adding these, that should be addition between them. You can't multiply those. We're going to do 3 plus 2 and get 5. And 1 minus 3, get negative 2. And this is our vector addition. The last one is if we have these two vectors, this is 3, 1, 2, negative 3. What we can do to add them is line them up tail to head. So essentially what I've done is one of the arrows is matching up with the tail. We call the part with the arrow the head, and the part without the arrow the tail. We can, like a coin. we have heads and tails. So you match one head to the other tail, and then overall, the final addition problem, the answer to the addition problem is from the remaining tail to the remaining head. In fact, what this will be is the same thing as going right 5 and then down 2. So that will match up with these. We said that we would go right 5 and down 2 overall. So this tail to head method, or adding corresponding components, you'll need to know both of them. So this was the summary for scalar multiplication. Distribute the scalar to each component. For vector addition, add the corresponding components. So some practice. If we define these two vectors, what we can do is say, okay, this is vector multiplication first, or scalar multiplication. So negative a is negative 0, negative 7, plus the vector 5, negative 11. To make this negative, we distribute in the negative. And now we can add the corresponding components. So 0 plus 5 is 5. 7 plus negative 11 is negative 4. So that's the vector. Same thing here. When we have 4 times this vector, we just distribute in 4 into both components. So this is negative 132, negative 8 squared is 34. 2 more. Now these are with unit vectors. They don't say that they're unit vectors, but typically we talk about I and j as our first 2 unit vectors. Square root of 2 is a scalar. We're multiplying it by negative 1, negative 3. I'm writing it this way. You didn't have to write it this way in order to do it. Negative square root of 2, negative 3 squared is 2. Or, more likely, the answer choices are written as negative square root of 2 I hat minus 3 squared is 2 j hat. Make sure that the j hat and the I hat aren't under the square root. Over here, we have negative u minus g. So we'll take negative u. Pretend those i's and j's are bold. It's really hard to write bold letters, in my opinion. That's why I prefer the other notation. 11i plus 9j. It's also kind of annoying when we have I as a complex number. It's kind of annoying to have both of those going on at once. 10 I hat plus negative j hat minus 11 I hat minus 9j hat. And now we add like terms. They're like components. So 10 minus 11 gives us negative 1 I hat. And negative j hat and negative 9j hat give us negative 10 j hat. So this is how we perform vector operations.